Good morning, student. Today I am here to discuss about a charge which is moving in a magnetic field. Before I start, student, let me revise certain points. Whenever there is an electric field, it exerts force on a charge given by this electric field is the external electric field, student, okay? It is exerting force on another charge given by this Q into E. For example, suppose there is a sheet of charge. Okay? It produces electric field in this direction. And now I have kept one positive charge here. It will exert a force on this direction, F is equal to Q. Now this force will be exerted irrespective of whether the charge is at rest or in motion. The force will be exerted. Okay, student? Now, student, what happens? Suppose here there is a magnetic field also. This is magnetic field, student. And now I have placed this charge. Now it is observed that there is no force act. Magnetic force is 0, student. But as soon as it starts moving charge, magnetic field exerts force given by which we have already studied. But in this case, student, again the force will be 0 because it is moving parallel to the magnetic field. If it starts moving this direction, then there will be a force. And you can find out by right hand rule. You can, student, find out. So what is the basic theory, student, is? The basic theory is a moving charge produces magnetic field. First thing, as well as electric field. Now suppose there is an external magnetic field. Then this field will exert force on this charge. And that force is given by, it is velocity, it is magnetic field, it is the charge, student. This is the theory which we have already studied. And this force is always perpendicular to velocity, it is always perpendicular to magnetic field. Now, student, based on this I will discuss one very important principle, a device known as velocity selector, student. It is the application of a force which exerts by the magnetic field on a moving charge. Suppose, student, we have arrangement like this. Here we have, this is the obstacle, this is the opening, and here we have another opening. Okay, student, and these are the obstacles, closed loop. This point I am naming it as P. Okay, student. Suppose in this region there exists a electric field. Okay, student, which is in the downward direction, and also there is a magnetic field. Already I told you meaning of this. What is the meaning of this cross sign, student? Perpendicular inside the board. Perpendicular inside the board. Okay. This is magnetic field, student. So this is the arrangement and this is the opening. Now here suppose we have arrangement of electrons of different velocity. Electrons of different velocities are entering this chamber from here. Okay, student? Many electrons are there of different velocities, V1, V2, like this. Now I am taking a particular electron. It is entering like this. First thing you see electric field, student. See electric field. It will exert force on the electron. Which direction? Opposite to the direction of electric field. So on this electron, the force, electric force, is upward direction, given by, because electric field is in the downward direction, it is a negative charge, the force will be on the upward direction. Now student, there is also a magnetic field. There is also a magnetic field. From the right hand rule, if you see, the electron is traveling in this direction and the magnetic field is inside it is inside, student. So from the cross product rule, if you observe it, the magnetic force will be in the downward direction, student, for electron. The angle between V and B in this case is 90 degrees, student. If you try from the right hand curl rule, you will see that the force on the electron is in the downward direction, student. So as I said, we have electrons of different velocities. Okay, student. Now suppose for a particular electron, of certain velocity, this force becomes equal. This force becomes equal, student. This means this get cancels, so I will get V is equal to so in this case the net force is 0. So this electron will travel straight and it will come out of the hole, student. And which electron will go out of the hole at P? Those electrons which have velocity equal to this ratio, E upon B. So what I said, student, in the starting, here we have electrons of different velocities. They are entering. So this electron will follow different paths. If this force is higher, it will travel in the upward direction. If this force is higher, it will travel here. But only those electrons will travel straight whose velocity becomes equal to E upon B, means net force will become, student, 0. So this means we have now a device which is known as velocity selector, student. Only electrons of particular velocity can be selected using this method. Those electrons are coming out, student. And student, this is a very historical experiment. This is the experiment by the help of which J. Thomson, one of the known scientists, have calculated this ratio for the electron by the help of velocity selector, student. Okay, student. Now for finding the direction of force, student, once again you can check. This is very easy. Electric field is in the downward direction. It is electron, negative charge. So force will be exerted in the upward direction. Now magnetic field is inside, student. Magnetic field is inside the board and the electron is traveling this side. Remember, it is a negative charge, student, negative charge. So the direction which will come by this rule, the electron will follow the opposite direction, student. So on that basis the force will come out to be, you can try it, student, by using your this hand. I told you two methods. Cross product rule. One method is this finger, first you have to place the hand like this. This finger will point towards the velocity. This finger will point towards the velocity. See, electron is traveling in this direction. This is velocity, student, this first finger. And this will towards the magnetic field. So in this case, if you see, student, this is the velocity. And these fingers are going inside the board, magnetic field. Now, perpendicular on the palm upward perpendicular. It is coming upward, student. Okay, that is the direction of force. But this is a negative charge. So the force will be downside, student. Okay, student, it is a very easy method. Again, I am giving you this finger. Place right hand like this. This finger should point toward the first vector. Which is the first vector? Velocity. And this forefinger should point toward the second vector. And what is the second vector? Magnetic field. So in this example, the first vector, electron, is traveling in this direction. So this is my first finger, thumb. And magnetic field is inside the board. So this is the second part of the hand, goes inside. So force is coming upward. But since it is an electron, the real force will be downward. So I have drawn it here. And angle is 90 degrees, so QVB. So this will act as a velocity selector, student. Let's, students, solve some more problem related to this. Suppose, student, we have again magnetic field inside the board and the charge is moving this way, student, positive charge. Very simple, student, use your right hand. This is the first vector, velocity. This is the second vector inside the board hand. Force is in the upward direction, student. Force is in the upward direction. Suppose, student, this charge is traveling inside direction of the board. Then how much is the force, student? It is 0 because V and B are becoming parallel. If the charge is moving inside the board, the force will be 0. Similarly, if the charge is coming outside the board, again the force will be 0, student. Because in both the cases, V is parallel or anti-parallel to magnetic field, student. Like this, student, you can take some other example. You take the magnetic field to be outside. Again, you can see it. Suppose the magnetic field is outside the board. Dot. This is magnetic field. Okay, it is perpendicular outside the board. Okay, student. Here again the charge is moving in this direction. Positive charge with velocity v. How will you keep the finger, student? This first vector is in the same direction. but my this finger, it is outside, so now it should come like this, student. See, this is first velocity traveling right side, and this finger is coming outside the board, student. Magnetic field is outside. Which side the force is exerted? Downward, student. This is the magnetic force which is existing. So whenever a charge moves in a magnetic field, student, the force will be exerted on that charge according to this rule, cross product rule. There is a vector product, student. And two cases forces are zero. First case, when charge is at rest, and second case, when charge velocity is parallel to magnetic field. In both these cases, student, force is zero. Now, student, suppose there is a current carrying wire. Suppose there is a current carrying wire. And here is the charge. Now, students, since the electrons are moving inside the wire, but there are proton also, positive charge also. So in this wire, net charge is zero. So net charge zero means this current carrying wire cannot exert electric force on this charge. Current carrying wire cannot exert electric force on the charge because net charge is zero. But student, if this charge starts moving, the same current carrying wire can exert magnetic force. Can exert magnetic force. And what will be the direction and how to find out that force, student, we will do it in next class. So till that, student, revise it thoroughly, this method.